For hundreds of years, man has used fire as a means of improving his lifestyle. We use it to change the shape of metal, to turn a solid into a liquid and a liquid into a gas. We use its light to see in the dark and its heat to warm us and to cook our food. We even use its energy to take us to the stars. For centuries, fire has been one of man's favourite tools. But as with any hazardous material, the potential for disaster is always present. To understand fire, we need to know something about the process of oxidation. This burning candle and this piece of metal are both undergoing the same process of oxidation. Both these substances are reacting with oxygen to form new substances. Only they're doing it at vastly different rates. This candle will oxidize fairly quickly, whereas this piece of metal will take many years to have fully oxidized. When the process of oxidation takes place fast enough for both heat and light to be released, we call that process fire or an explosion, depending on the speed of the reaction. Fire is rapid oxidation, whereas an explosion is a very rapid fire. As different substances oxidize at different rates at different temperatures, some are more of a fire hazard than others. We'd hardly think of this piece of metal as a fire hazard. This chart shows the different temperatures at which substances burn. Those which need extremely high temperatures to burn are the safer in terms of fire risk. The substances that will burn or explode at very low temperatures are a much greater fire risk. There are three essential ingredients needed to generate a fire. They are firstly fuel, or a substance to burn. Secondly, oxygen must be present. And finally, there must be a source of heat sufficient to initiate the process. These three essential elements are commonly referred to as the fire triangle. All three components of the fire triangle are required to produce and sustain fire. So we'll look at the role of each one separately. All organic substances will oxidize. Organic substances are those that result from living matter, such as timber, living tissue, petrochemical products such as oil, plastics or bitumen, and fabrics and fibres. Most common inorganic substances do not burn readily, if at all. It's important to note that it's not the substances themselves that burn, but the vapours that come from them. Notice in the burning of this match that the flame sits above the burning wood. That's because it's the vapours coming from the decomposing wood that are burning. The fact that it's vapours that burn is particularly relevant to flammable liquids. It's not the liquids that burn, but the vapours given off by them. To demonstrate this, a measured quantity of petrol is poured into this container. We all know that petrol is a fire hazard, and we all believe that petrol burns. But look, when the vapour is ignited, the surface of the petrol doesn't burn. Only the vapour burns. This point becomes even more apparent when kerosene is used. We all know of kerosene as a heating fuel and have no doubt that it'll burn. But when a lit match is dropped into the kerosene, there is no fire. The reason is that it's not the kerosene that burns, but the vapour that comes from it. And at room temperature, the kerosene does not release enough vapour to burn. Now, if we heat the kerosene, it soon reaches a temperature where enough vapour is given off quickly enough to be ignited. Notice once again that it's the vapour that's burning, not the kerosene. If the same quantity of petrol is placed in containers of different size, the larger container will allow more vapour to escape because of the increased surface area of the liquid, and hence a larger flame will be able to be ignited. This is an important consideration in dealing with and safeguarding against fire. The term we use to describe the temperature at which flammable liquids release enough vapour to be ignited by a source of ignition is flash point. The flash point for petrol is minus 40 degrees Celsius, which is well below room temperature, but the flash point for kerosene is 38 degrees Celsius. When a substance has reached a temperature where it continues to burn, it is said to have reached its fire point. Although the fire point is a higher temperature than the flash point, it can be sometimes reached through the heat generated by ignition of a flammable liquid at the flash point. Another temperature needing to be defined is the temperature at which a substance will ignite spontaneously, or self-ignites. This is called the auto-ignition temperature. Obviously, any substance with a low flash point, fire point or auto-ignition temperature is a high fire risk and needs to be handled with appropriate care. It is also important to be aware that all flammable vapors are heavier than air and so will tend to run downhill from the source and settle in low-lying areas. This makes low areas a greater fire risk than others. A pit or service bay may be the site of a potential disaster, and so appropriate care should be taken. As we can see from this Bunsen burner, gases are already vapors, and so they will ignite at room temperature. Heating substances will release flammable vapor, but there's also another way that a liquid can be turned into vapor. When a liquid is atomized, vapor levels increase. We've already seen that kerosene at room temperature does not release enough flammable vapor to be able to sustain a fire. But if a fine mist of kerosene is sprayed into the air at room temperature, sufficient vapor is released to create a momentary flame. Yet another factor in considering fuels is the role of dust and powder. Dust can act like vapor given the right conditions, and fires have resulted from atmospheric dust as well as dust build-up on surfaces. Small particles vaporize or oxidize much more readily than the same matter in larger particles. To show you just how much more flammable dust is to larger particles, watch what happens when iron filings are sprinkled onto this flame. A sheet or block of metal does not burn, but tiny particles of iron will burn or oxidize quickly and brilliantly. It's interesting to note that fires occur most frequently in industries we would regard as having a relatively low fire risk in terms of combustible or flammable fuels. So we cannot become complacent even if there are no highly flammable fuels in our environment. Another component of the fire triangle is oxygen. Because oxygen makes up 21% of our air, it's readily available and very hard to eliminate. In addition to the oxygen in the air, many chemicals release oxygen in some form or other as they break down. And in some cases, the substances being oxidized release oxygen which feeds the process. Having fuel and oxygen does not make for a fire without the application of a source of ignition or heat to get the combustion process started. The source of ignition may also be called the initiation energy because it is responsible for initiating the combustion process. Sources of ignition are many and varied but fit into four broad categories. 1. Production heat. 2. Faults. 3. Electrical spark. And 4. Creature comforts. Production heat includes all manner of hot processes such as heat to cook something, shrink wrap or seal containers, make something malleable, or heat a substance. Steam, flame, hot air and radiators all fit this category. Then there are chemical reactions which are part of the production process and which generate heat. Hand tools not only generate heat and sparks, but can throw sparks for many meters. Sparks are white hot particles. Hot tools such as oxycutters and arc welders also produce heat and sparks, and hot equipment such as motors, transformers and the like also create a fire hazard. Under the heading of faults are such heat-generating problems as friction from a seized bearing or unlubricated or faulty part. An unwanted chemical reaction would also fit this category. Electrical spark includes spark from electrical contacts such as on-off controls, internal switchgear and contact points. Electrical bushes and similar contact points such as in electric motors for drills and saws also produce electrical sparks. Because even a tiny spark can create fire in a vapor-rich atmosphere, static electricity must be included in this category also. Creature comforts includes lighting, which can generate sufficient heat to start fires, heaters to warm people or their food, and cigarette butts, matches and the like, which also contribute to many fires. Now that we've reviewed the three components of a fire, there's one more factor to consider. Fires will only start or be sustained if there's the right mix of the ingredients. The term limits of flammability denotes the range of vapor concentrations in air over which combustion can occur. If the fuel to oxygen ratio is right, and in a confined space, we have the ingredients for an explosion. To show you how this works, 3 drops of petrol are placed into the spark tube. Mixed with the oxygen and sealed in the tube. Now, as the spark is ignited, you can see the result. But if the experiment is repeated by placing more than 3 drops of petrol into the tube and shaking the mixture, sealing the tube and firing the spark, there is a different result. A fire not only needs the 3 components of fuel, oxygen and a source of ignition, but it must have them in the right mix. To summarize, we have seen that fire is really only the process of oxidation taking place rapidly. We know that fuel, oxygen and a source of ignition are required for fire to be initiated. To establish the measure of fire risk, we ask the question, at what temperature does a substance give off sufficient vapor for ignition? We call that temperature the flash point. It is the vapor that burns, not the substance in most cases. Heating a substance releases vapor which can be ignited. Substances which ignite at low temperatures are the greatest fire risk. Now that we've looked at what fire is, we can look at ways of safeguarding against it. And to do that, we'll consider the 3 components of the fire triangle again. Fire prevention is based on keeping the 3 components of the fire triangle apart and not allowing them to come together. The first comment to make is that we must know what we are dealing with. It pays to know something about the flash point, auto-ignition properties and special storage requirements of the substances. Many fuels require special handling, such as airtight or vacuum containers, cool store conditions, specially designed storage areas, fuel lines and the like. Be sure to observe all special requirements faithfully and consistently. Containers and fuel lines must be kept in good order, with attention paid to leaks of fuel, vapor or spray. Good ventilation is important where vapors are likely to be a risk factor, and this includes low-lying areas where vapors tend to accumulate. Good housekeeping is also important, ensuring that dust, rubbish and combustible materials are not allowed to accumulate, and also ensuring that passageways, fire exits and firefighting equipment are not blocked or obstructed. Another precaution is to store fuels in such a way as to be able to separate them and thus reduce the volume of fuel should there be a fire. As we've already seen, oxygen supply is very difficult to control because oxygen is so readily available in the air we breathe, and also because it can be produced chemically. Substances providing a ready supply of oxygen include peroxides, acids, pool chemicals, bleaches, and fertilizers. In some cases, some chemicals can take the place of oxygen and also allow fires to occur. To prevent fire, it's important to keep fuels away from oxidizing materials, such as those mentioned. Controlling the sources of ignition is possibly the area where the greatest gains can be made in fire prevention. A watch should always be kept for items placed too close to lights, heaters, hot processors, stoves, and the like. Remembering that heat travels upward, attention should be paid to what is above the heat source, not just what is near it. Care should be taken to control static electricity, as is done by providing an earth to stop build-up of static charges. People using electrical tools should exercise particular care of both internal electrical sparks and sparks created by their use. Staff should also take the risk of fire from smoking very seriously, and all smoking regulations should be observed carefully. This chart shows a comparison of the most common causes of fire. Being aware of the role of the 3 ingredients and looking out to safeguard against fire will go a long way to reducing the risk in your environment.